Some time ago, I saw a video by a famous YouTuber in which his young son also appeared. To demonstrate the child's intelligence, his father mentioned random dates from the 20th century, and the child named the corresponding day of the week. January 17th, 1935. Thursday, the child said without hesitation. October 23rd, 1960. Sunday, the child said confidently. Along with this, the YouTuber showed a calendar with the date in question, proving that the child had answered correctly. Intrigued by how the child was able to do this, I searched the internet for methods or algorithms to obtain the day of the week for any date. I saw that there are several interesting ones, but I could not find any mathematical proof for any of them. In this video, we will demonstrate a mathematical formula that will allow us to obtain the day of the week for any date. And also very interesting, to achieve this, we will use modular arithmetic, a very interesting area of mathematics with many applications, this being just one of them. We will also simplify this formula so that we can mentally calculate the day of the week for any date in the 20th century, just as the child did. Let's start by taking any month and year. For example, July 2025. We see that July 1st is a Tuesday. We will prove that knowing this information, it is possible to know the day of the week for any other day of the month. To do this, let's take the days of the week and place them on the perimeter of a circle in clockwise order. Suppose we want to know what day of the week July 5th corresponds to. Well, since July 1st is a Tuesday and July 5th occurs 4 days later, we can count 4 clockwise movements from Tuesday. So we conclude that July 5th is a Saturday. We check the calendar to confirm that this is correct. Now suppose we want to know the day of the week for July 30th. Since July 30th occurs 29 days after July 1st, we would have to count 29 days from Tuesday to see that July 30th is a Wednesday. We also verify that this is correct. Although we obtain the correct result, counting 29 times is not a very elegant or convenient method. To find a more elegant and simple method, we assigned each day of the week a number between 0 and 6. So from now on, day 0 will be Sunday, 1 Monday, 2 Tuesday, 3 Wednesday, 4 Thursday, 5 Friday, and 6 Saturday. For calculation purposes, we will no longer refer to the days of the week as Sunday, Monday, Tuesday, etc., but rather as day 0, 1, 2, and so on up to 6. Therefore, July 1st will no longer be called Tuesday, but rather day 2. Let's repeat what we did previously. July 5th, which occurs 4 days after July 1st, corresponds to day 6, or Saturday. Here comes the interesting part. We could obtain this result by directly adding 4 to July 1st, which was day 2. We add 4 because July 5th occurs 4 days later, and we get the correct result, 6. Let's look at another example, July 11th. Since this day occurs 10 days after July 1st, we add 10 to 2, obtaining 12 as the result. But this result is strange, since there is no day 12. There are only days from 0 to 6. To see how we fix this, let's replace 10 with 7 plus 3. Let's see what it means to add 7 to day 2 in our diagram. Counting from day 2, 7 movements, we see that we end up back at day 2. In a sense, adding 7 to 2 gives the same result, 2. It is as if 7 were 0. Taking this into account, we would only have to add the remaining 3, giving a result of 5. Thus, we confirm that July 11th was indeed day 5, or Friday. Another example is July 19th. Since this occurs 18 days after July 1st, we would have to add 18 to day 2, obtaining 20. Again, date 20 does not exist, so in this case we write 18 as 7 times 2 plus 4. However, adding 2 times 7 to 2 means adding 7 and then adding 7 again, which again gives us 2 as the result. We have already seen that adding 7 once is like adding 0, but now we see that adding 7 twice is also like adding 0. So then we finally add the remaining 4 to obtain 6 as the solution. This means that July 19th is day 6, or Saturday, as we can verify. We are now in a position to write our first mathematical formula that will bring us closer to our goal. Let the first day of the month, M, and the year, Y, be written in this way, which can take values between 0 and 6, corresponding to the days of the week between Sunday and Saturday. Therefore, the day of the week corresponding to the nth day of the same month, M, and year Y, can be obtained by adding n and subtracting 1, since the nth day occurs n-1 days after the first day. But this is not just any sum. It is a special sum that we denote by adding mod 7. What does this mean? It means that if the term in question can be written as a multiple of 7 plus another term, where specifically alpha is an integer and beta is an integer between 0 and 6, we must disregard the multiple of 7 and only keep beta. We can do this because, as we saw, adding a multiple of 7 is like adding 0. So we can say that the day of the week is beta. The notation we have introduced has to do with an area of mathematics known as modular arithmetic. Specifically, when we have this expression with x and y as integers, as is m, we say that x and y are congruent modulo m. But what does this mean? It simply means that the difference between x and y is any multiple of m. This definition and its respective notation were first introduced by the Prince of Mathematics Carl Friedrich Gauss in 1801 in his publication Disquisitiones Arithmeticae. Gauss's genius in this notation has to do with the similarity between the properties of congruence modulo m and the properties of equality. In fact, both have the same properties. For example, every integer is congruent to itself. Another example, if x is congruent to y, then y is also congruent to x. Furthermore, if x is congruent to y and y is congruent to z, then we can say that x is congruent to z. All these properties can be demonstrated with the definition of congruence that we have shown here. One property that we will use quite a bit in this video is that if we have that x is congruent to y plus z, and z is congruent to w, then we can substitute z for w in the first relation to say that x is congruent to the sum of y plus w. The similarities between the notion of congruence and equality are complete, so we can say that the congruence modulo m sign respects the arithmetic operations of equality. We can conclude that every time we see a congruence sign, it is as if it were an equal sign. Let's summarize what we have so far. If we want to know the day of the week for the nth day of month M and year Y, we must add the day corresponding to the first day of that month and year to n and subtract 1, disregarding all multiples of 7. For example, we can apply the formula to find the day of the week for December 23rd, 2006. But here you may ask yourself, how can we find out the day of the week for December 1st, 2006? Well, let's suppose we know the day of the week for the first day of 2006. We will see that knowing this information, we can find out the day of the week for the first day of every month. Let's see how. First, we know that January 2006 has 31 days. Therefore, February 1st of that year occurs 31 days after January 1st of that year. So to get the day of the week for February 1st, take the day of the week for January 1st and add 31 in modulo 7. Since 31 is 7 times 4 plus 3, we disregard the multiple of 7, so we only need to add 3. All right, let's continue. Now, the 1st of March 2006 occurs 28 days after the 1st of February, since February has 28 days. So we get the day of the week for March 1st by taking the day of the week for February 1st and adding 28 modulo 7. But the day of the week for February 1st is congruent with the day of the week for January 1st plus 3. We then substitute this into the second formula to leave everything as a function of January 1st. Since 28 is 7 times 4, we can disregard it to obtain the following relationship. We could continue with this procedure to obtain the corresponding formulas for the days of the week on April 1st and May 1st. In fact, we can do the same for all the remaining months, writing the day of the week for the first day of each month based on the first day of 2006. Let's organize this so that what we have obtained is a little clearer. For each first day of each month, we must add a different number to the day of the week of January 1st. Knowing that any number is congruent with itself, we can include January 1st in the list by including a 0 in the number column. Now we can answer what day of the week corresponds to December 1st, 2006. We simply add January 1st, 2006 plus 5, and as usual, all this in modulo 7. Now, generalizing this for any month M, we should add the number corresponding to each month, which we will call C of M. We can organize these values in a table that we need to know for our purposes. It is now that the following question may arise. Can we generalize this formula for any other year? For example, for the year 2008? The answer is yes, but we must consider something very important. In 2006, February had 28 days, as is the case for most years, which we will call normal years. For all these years, the table of values will be the one shown in the table, which is why we have added a subscript n to indicate that this table is valid for normal years. However, 2008 is different, since February has 29 days, one more than normal years. This is true for all leap years. Because of this, the table of values for each month changes from March to December. If we refer to these values with a subscript L, indicating their validity for leap years, we can see that their table of values does not change for the months of January and February, but it does change for the months of March to December, requiring the addition of an extra day due to the additional day in February of leap years. Let's summarize what we have so far. We have a formula to obtain the day of the week of the first day of month M and year Y, which depends on the day of the week of January 1st of year Y, plus values that depend on the month in question and also on whether the year is normal or leap. Let's recall the formula we had previously. We now know that the day of the week of the first day of month M and year Y is congruent with the sum shown. So by combining both formulas, we have a relationship that brings us closer to our final goal. We are getting closer little by little. The day of the week of the nth day of month M and year Y depends on the corresponding nth day, which is known once the date is given, of course. It also depends on the value C of M, which is also known by looking at the table. However, we still need to know how to obtain the first day of January of the corresponding year. Our goal now is to find out the day of the week on January 1st of any given year. To do this, we will assume that the Gregorian calendar, which is the one we currently use with all its months and number of days in each month, has been valid since the beginning of our era from the year 0 onwards. I know what you're probably thinking, that this is not true since the Gregorian calendar was promulgated by Pope Gregory XIII in 1582. Some countries began to use it that same year and others years later. But we could say that, in general, starting in that year, 1582, the Gregorian calendar began to take effect. However, here we will assume that this calendar began to govern from the year 0, simply to facilitate mathematical calculations. But we must be aware that the formula we obtain in the end will only be valid for dates after the Gregorian calendar began to govern, after the year 1582. Let's return to our objective. Let's assume that the day of the week of January 1st of year 0 is known. We will now see how we can obtain the day of the week of January 1st of each year based on this day. For example, January 1st of the year 1 occurred 365 days after January 1st of the year 0, since each year has 365 days. So, to find out the day of the week of January 1st, year 1, we must add 365 to the day of the week of January 1st, year 0, as always in modulo 7. Now, we know that 365 is 52 times 7 plus 1, so we disregard the multiple of 7 and keep the 1. Similarly, to obtain the day of the week for January 1st of year 2, we add 1 to the day of the week for January 1st of year 1. Since this variable is congruent with the sum of the day of the week for January 1 of year 0 plus 1, we substitute this into the formula to obtain the following expression. Similarly, we obtain the following relationship for the year 3, the year 4, etc. The generic pattern is quite simple to observe. We can therefore conclude that the day of the week of January 1st of any given year is the sum of the day of the week corresponding to January 1st of the year 0 plus the corresponding year, modulo 7. However, this formula is incomplete. Let's see why. In our calculation, we assumed that all years have 365 days, but we know that this is not true, since there are leap years that have an extra day. How would this affect our formula? Well, let's suppose that we are interested in knowing the day of the week of January 1st of a given year. We know that before the year, there will be some leap years. Since each leap year has an extra day, we need to know the exact number of leap years prior to the year, a number we will call L of y. And that number must be added to the expression found previously. Now the question is, how do we know how many leap years there are before a certain year? To do this, we need to know the definition of a leap year. Firstly, leap years occur every 4 years and are those years that are divisible by 4. Let's calculate the number of leap years before the year 6, for example. Since leap years occur every 4 years, we are tempted to write 6 divided by 4, but this results in 1.5, which is not a whole number. To save the situation, we introduce the ceiling function. The ceiling function of x returns the smallest integer greater than or equal to x. This definition may seem complex, but you will understand how simple it is with examples. The ceiling function of 9.1 is 10. The ceiling function of 6.3 is 7, while the ceiling function of 8.7 is 9. In other words, if the argument is a decimal, this function assigns the integer value that follows the decimal. Finally, if the argument is an integer, the function assigns the same argument. For example, the ceiling function of 4 is 4. With this definition, let's apply the ceiling function of 6/4, obtaining the result 2. This result is correct, since before the year 6, there would be 2 leap years. Let's look at another example, the number of leap years before the year 13. Let's calculate the ceiling function of 13 over 4, obtaining 4, which is the correct answer. We are therefore confident in writing the following relationship. But that's not all there is to leap years. Let's say we want to find the number of leap years prior to the year 440. Well, we already have our formula, so we simply apply it to get 110 as the result. However, this result is not correct, since those years divisible by 100 are not leap years, despite being divisible by 4.
So we must subtract these years from the calculation. We do this by subtracting the ceiling function of 440 over 100, thus subtracting the 5 years that are not leap years. Therefore, we correct our generic formula.
But the story does not end there. I know it's not pleasant, but it's not my fault. It's Pope Gregory XIII's fault. We have to add a new correction because although those years divisible by 100 are not leap years, those that are divisible by 400 are. So the years 0 and 400 are leap years again. To add this correction, we simply have to add the ceiling function of the year over 400. But that's not all there is to say about leap years. Just kidding. This is the final relationship for L of y. Let's now recall the master formula we had previously. We now know the day of the week of January 1st of the year y, which is congruent with the sum of the 3 terms shown. Replacing in the master formula, we have the following formula. Given a particular date, the nth day is known. C of m is known from the table by knowing m and whether the year is normal or leap. And we also know y and L of y. We just need to know what day of the week January 1st of the year 0 would have been. To answer this question, let's consider a particular day on a calendar and apply the formula we have to solve our unknown. Let's take January 1st, year 2000, which was a Saturday, or day 6. Let's apply our formula to that particular date. We add the day of the week corresponding to January 1st of the year 0, which is our unknown. We add the year 2000, the number of leap years prior to the year 2000. Cn and Cl are the same for the month of January, 0. And finally, we consider the nth day, which is 1 in our case. We simplify the expression a little, calculate L of 2000, replace it in the expression, and obtain the following. Noting that the number obtained in the expression is a multiple of 7, we disregard it and obtain that the day of the week of January 1st of the year 0 would have been the day 6, that is Saturday. We are almost ready. We replace this value in the formula and simplify the expression to finally obtain our wonderful mathematical formula that allows us to obtain the day of the week for any date in the Gregorian calendar. Let's apply an example. A very important date in the history of mathematics is the birth of our beloved Carl Friedrich Gauss, considered by many to be the greatest mathematician in history. Gauss was born on April 30th, 1777. We simply substitute the values into the formula. Noting that Gauss was born in April of a normal year, we must consider C sub n of 4, whose value is 6. Working through the calculation, we discover that the Prince of Mathematics was born on a Wednesday. Amazing!
All right, so we have our master formula. We could end the video here, but there's still something left to do. Let's go back to the beginning of the video, where I mentioned that a young child was able to mentally calculate the day of the week for any date in the 20th century. This raises the question, can we simplify our formula so that we can do the calculation mentally just like the young child did? Let's see. N is a number between 1 and 31, which seem to be simple numbers to manipulate mentally. C sub n or C sub L are also mentally manageable numbers, although unfortunately we will have to memorize 2 columns of numbers, which doesn't seem very good. But the situation is much more complex when working mentally with terms related to the year, because usually they are very large numbers. Imagine, for example, working with the year 1945. We will therefore focus on simplifying these numbers. First of all, we will only work with years from the 20th century, that is, years from 1900 to 1999.
So we can write the year y in general terms as the sum of 1900 plus a variable g, which can take values between 0 and 99. As usual, we can write 1900 in such a way that we can disregard all multiples of 7, finding that the year y is congruent with the sum of 3 plus g modulo 7. Now let's take the following term, which involves the ceiling function of y over 4. Developing the calculation, we obtain the following. And here, we consider a useful property of the ceiling function. The ceiling function of the sum of a natural number with any other number is equal to the sum of the natural number plus the ceiling function of the other number. In simple terms, natural numbers come out of the ceiling function. Applying this to our case and disregarding, as always, the multiple of 7, we obtain the following congruence relation modulo 7. We repeat the same for the term y over 100, obtaining another congruence relation modulo 7. Finally, we repeat the same procedure for the case where y divides 400, but here there is an interesting subtlety. Considering that g can take values between 0 and 99, we can manipulate the inequalities to show that the term that is the argument of the ceiling function is a number greater than 3/4 and less than 1. Therefore, the ceiling function of that argument will always be 1. We then obtain the following equality. Replacing these four expressions in our master formula, we obtain the following simplified formula. We must remember that this formula is only valid for years in the 20th century, with g being the number formed by the last 2 digits of the year. We have already simplified the expression considerably, but we can simplify it even further. Before looking at this, we need to understand another special function known as the floor function. The floor function of a variable x returns the largest integer that is less than or equal to x. To understand this better, let's look at some examples. The floor function of 3.9 is 3, of 8.7 is 8, and of 5.2 is 5. In other words, if the argument is a decimal, it returns its integer part. Now, if the argument is an integer, the ceiling function returns the same integer. For example, the ceiling function of 9 is 9. Let's quickly compare this floor function with the ceiling function we saw recently. The ceiling function of 3.9 is 4, of 8.7 is 9, of 5.2 is 6, and of 9 is 9. Comparing each of these results, we conclude that both functions are the same when the argument is an integer, but when the argument is a decimal, the ceiling function is the floor function plus 1.
Let's apply this to the ceiling function of g over 4. We note that the condition that g over 4 is an integer is equivalent to the year being a leap year. On the other hand, g over 4 not being an integer is equivalent to the condition that g is a normal year. This is the first point to highlight. The second point has to do with the relationship between C of L and C of N. We know that C of L is greater than C of N by 1 unit for the months of March to December, while they are equal for the months of January and February. This is our second important point, which we will use later. On the other hand, the ceiling function term of g over 100, knowing the possible values of g, can take two values, being 0 when g is 0, and 1 in all other cases. Remember that g equal to 0 corresponds to taking the year 1900, and g different from 0 corresponds to taking the years between 1901 and 1999.
Very well. Let's separate our analysis into two cases. First, when g is not equal to 0. In turn, we subdivide this case into two cases, normal year and leap year. Let's look at the normal year first. In this case, we must take C of n, we take the relationship corresponding to the normal year between the ceiling and floor functions, and finally the ceiling function of g over 100. With all this, the simplified formula is reduced to the following formula. All right, now, even within the case g different from 0, let's consider the case of a leap year.
we take the corresponding relationships and also consider the months between March and December. For this situation, we obtain the same simplified expression as before. Now, for the months of January and February of a leap year, the relationship between C of L and C of N changes, meaning that in these cases, one must be subtracted from the simplified expression.
Let's summarize this so as not to get confused. For the day of the week corresponding to any year between 1901 and 1999, we have the following simplified expression which works in general. However, the only exception is that if the months are January or February and it is a leap year, we must subtract 1 from the previous result. Finally, the second case, which is much simpler to analyze, is when G is 0, that is, the year 1900. In this case, G over 100 is 0. Now, to know whether to use C of N or C of L, we must know whether the year 1900 is a leap year or not. 1900 is divisible by 4, so it would be a leap year. However, it is also divisible by 100, so it loses its leap year status and becomes a normal year. Finally, it is not divisible by 400, so it does not change to a leap year and remains a normal year. Therefore, we must use C of N in the simplified formula. We then note that the same formula for the years between 1901 and 1999 is also valid for the year 1900. So then we have our final reduced formula, along with the exception that must also be remembered if you want to do the calculations mentally. Remember that this formula is valid for any year of the 20th century, where G represents the number formed by the last 2 digits of the year. Since our formula depends only on C of N and not on C of L, the latter column can be disregarded, and so we only need to memorize 1 column instead of 2. Now let's think about how the child could have calculated the date mentally. The YouTuber father told him January 17th, 1935. First, the child could have thought, well, G is 35, which is 7 times 5, so we are left with 0. Now we have to calculate the floor function of G over 4, that is 35 over 4.
This seems complicated to do mentally, but it's not if we follow this trick. First, the complexity lies in the fact that 35 is an odd number. The calculation would be simple if the number were even. Well, since we are working with the 4 function, whenever we have an odd number in the numerator, we can subtract 1 to get an even number, in this case 34. Since we are dividing by 4, we first divide by 2, leaving 17, which we must divide by 2 again. But we apply the trick again since 17 is odd, we subtract 1, leaving 16, which divided by 2 is 8. Perfect. Now we see that 8 is 7 plus 1, we depreciate the 7, and we are left with only 1, which added to the 0 we had before is 1. Now we must add C of N for month 1, whose value is 0. Then we must add N, which in this case is 17, to obtain 18. 18 is 14 plus 4, and since 14 is 2 times 7, we discard it, leaving 4 as the final result. Although the date corresponds to January, 1935 is not a leap year, since 35 is not divisible by 4. Therefore, the exception does not apply, and the final result is 4, which is Thursday, as the child correctly stated.
I hope you enjoyed this video. Comments, constructive criticism, and suggestions are welcome. I hope to upload more videos soon, so see you next time.